Hello everybody. So today we're going to talk about networks, graphs, and in particular a novel way of looking at networks, analyzing them that may find quite useful applications. Something that I call scale-specific network geometry. And we will dig into it in a second, but first the query of the day. It's a kitchen sponge. Now, most people might think like, well, there's nothing quite remarkable about these, but well, first of all, I would usually, be very hesitant to use the kitchen sponge, all of the bacterial cultivations and God knows what else. But this one is completely unused. Just, took it out of the package without ever using it. And I'm finding the experience of touching something that would otherwise be quite, dirty and unhygienic, quite funny, to be honest. Like, I feel like I should be washing my hands, but on the other hand, like the rational part of my brain reassures me that no, it's actually fine. Now, the sponge will also become relevant later in the video because it has a particular network geometry that is relevant for the conversation. But I'll leave that here for now. I've got my notes as usual, so we will go through them. Okay, first of all, you probably know what a network is. I usually use the word graph, especially with people who, like math, but because oftentimes when I say graph, people might just confuse it with something like, X, Y axis. But no, really, I mean these mathematical objects that are nodes connected by edges. And I'm a big fan of graphs. I've really been very interested in them for a while. When I was a kid, it was mind blowing, like the Euler's property of graphs, and like finding interesting proofs. I used to love graph problems when I was in math competitions. It was, something about it, the combinatorics of it. It's quite fascinating. Now, I'm also quite acquainted with graphs in a different sense, which is that there is graphs, in kind of a mathematical, proof-based way, which, pure mathematicians are really interested in. But then there's also kind of like graphs in a statistical sense where you look at a huge network, a huge empirical network, something that you actually measure from the world, and you're trying to tell identify interesting properties of it, interesting things that you may do something useful with them. And one example of that is like my first professional experience was an intern at this startup that was called Klout. Quite a fascinating, slightly controversial, but like honestly really interesting startup, like in 2011, I believe, that what they did is like, this was opt-in completely in that, like, if you agreed to the terms of service of Klout, they would basically look at your social connections in all of your, as many social networks as you granted them access to. At the time it was LinkedIn and Squarespace, and I forget if Instagram was there, but like, for sure Twitter and Facebook and Google Plus, for sure. Google Plus, rip Google Plus. And then what they would do is they would analyze this massive graph of every user who had opt-in and identify kind of this notion of social capital, which, cashes out into something actually kind of recursive, right? Because it's not only what are the chances that somebody will act upon your suggestions, but also what is the social capital of the people who will act upon your suggestions. So as an example, if you're a Twitter user and you only have one follower, but that follower is, let's say, somebody extremely famous. I'm just gonna throw in out there Justin Bieber, simply because he was at some point, the top clout scorer in the world, with a clout defined as 100. Later on, other people became the most popular person on social media, but at the time it was Justin Bieber. If Justin Bieber is following you in Twitter, that will just skyrocket your clout score. And if Justin Bieber retweets something that you say, even if he's the only follower you have, yeah, you're gonna have a huge clout score. Now, clout scores are quite interesting. They find some dystopic applications, with something like a social credit score. They also find quite a few really potentially quite, good applications that save lives, and I'll give you an example in a moment. Before I get into that, I also wanted to mention that, some of the perhaps the best resource for statistical graphs in particular that I know of is this class by Jure Leskovic at Stanford, a class that I took many years ago. Is CS224W. There's a link in the description, and you can find it. And all of the lectures from the previous years are freely available online, as well as the problem sets and the handouts. And if you want to get it up to speed on how to analyze graphs and say interesting things about them, that is the place to go from my point of view. It's just fantastic course. And a lot of the ways in which I think about statistical graphs really come from that course, and then like reading the literature. Also, ultimately I do have a little bit of a further, like more professional background in graph analyses. And even my master's thesis ended up being about basically analyzing the network of transition probabilities between emotions and the graphical properties of that, identifying attractors in that space. And there's a lot of fascinating things to be said about that. Okay, so that's kind of my background. I guess I wanted to say one more thing about like the mathematical kind of like proof-based graphs, which is like it's a really good question. Like, for a given number of nodes, how many graphs are there? And that's a really difficult question, actually, because of the symmetries that exist. Why? Intuitively, you may think it's, well, for every pair of nodes, you could or could not have a graph, an edge in there. And so therefore is like, number of possible edges, which is like n times n plus 1 over 2. And basically 2 to that, because every edge could be there or could not be there, might not be there. And like, that means that total number of possible graphs is 2 to the n times n plus 1 over 2, which is huge. This grows very quickly. This is, an exponential to the quadratic function, and it grows really fast. Now, there is a complication there, which is that you might be double counting a bunch of graphs. In fact, the simplest example is when you have just 3 nodes, let's say like A, B, and C. You have the issue that if A is connected to B and B is connected to C, that actually is, an equivalent graph topologically as A connected to C, which is connected to B. Basically, you can label the one in the center as A, B, or C, and so you have like 3 possibilities. And that is not accounted for, in that way. So it's actually a really difficult problem, how many graphs there actually are, which connects to this whole idea of graphlets, which is like, the number of irreducible, like once you take into account the possible symmetries of a small graph, how many are there for a given number of nodes? And I highly recommend digging into it. Graphlets are also really useful, not only kind of in the pure math domain, but also when it comes to analyzing statistical graphs. Although that's a rabbit hole, and I'm not going to talk about it today, maybe another day. Okay, so know your graphs. What kind of graphs are there, especially when we're talking about like, large scale statistical graphs? And I'll just mention a few. Those of you who are interested in graphs, you've already heard them, but it's good to kind of like, go over them. First of all, we have kind of these geometric graphs, which is graphs where basically each node is kind of embedded in a geometric space and it's connected to other nodes. You could even make it, in a regular lattice or something like that. And a very neat property of that is that, if you start at one node and then you count how many nodes you can arrive as a function of the number of steps that you can make, that will grow with basically an exponent that is the dimensionality of the space. If you have a planar geometric graph and you start kind of like making jumps from a central node, you will be able to get to something that is proportional to n square, where n is the number of jumps. If you're in a Euclidean 3D space, the number of nodes that you can arrive at is going to be n to the cube. Okay, so you get the idea. There is kind of an interesting twist to this, which is small world networks, which is like if basically you have, a geometric graph like that, and then you randomly shuffle some of the edges such that like, randomly you take some of the nodes and you add edges to them. Very quickly, you will see that the speed at which you can arrive at other nodes as a function of the number of jumps starts to go from this kind of polynomial n to the, whatever dimensionality of the space, and it switches into, e to the n. Basically, really quickly becomes an exponential growth. Which, confusingly, a lot of people kind of tend to mistake small world networks and then these other things that are called scale-free networks, where basically there's a lot of ways of defining them, but roughly is like they're self-similar. In other words, like they look the same no matter what scale you're looking at them. And now those are like actually much more connected in a way than just a regular small world network. However, the exponential growth is the same. You will still have kind of this exponential increase of possible number of nodes that you can arrive at as a function of the number of steps. Now, what is the actual nature of like very large scale graphs? And a lot of people believe it's a scale world or small, scale free or small world, but it's actually neither. Jure Leskovec, precisely the same professor who gives CS224W, and his team, they have analyzed these gigantic graphs, gigantic social network graphs and ecological networks and, protein interaction networks, metabolic pathways, very different types of graphs that, when you get to the level of like millions and hundreds of millions of nodes and, many more edges than that, like the structure of it actually doesn't look scale free. It's more complicated than that. It's also not a small world. Is this weird thing where there is a huge, mega, ultra, super huge cluster in the center, kind of like a galaxy core. And then there is what he calls whiskers, which are kind of like little tentacles that are somewhat connected to the core. And that is like as much, large scale community structure as you can identify in these graphs, apparently. Also, I'll link in the description. It's, fascinating research. How do you actually tell what is the shape of, a super huge graph? And that's the way. I mean, it's fascinating research. Okay. Now, what am I going to talk about today that is new? Well, actually, this was sparked by, thinking very deeply when the pandemic was starting. COVID, around like February and March, I kind of like thought like, I wonder if there's like anything I could possibly contribute to this space. And that led to this article in Quality Computing called Quality Computing Coronavirus Edition, Toroidal planets and other cocktail napkin ideas. The cocktail napkin idea came from this quote from the movie Armageddon about, they're desperate, like the asteroid is like coming really soon, and they're trying to destroy it somehow. So they just ask like, I don't care where this is coming from. I don't care where the idea comes from. Even if it's written in a cocktail napkin, we will consider it. So these ideas that I was like throwing out there in that article were kind of like that. It's like, okay, this is like a long shot, but like maybe somebody will find it useful and interesting. And I did think at the time, and I continue to think, that it's a novel idea. More so that actually has been vindicated. I've actually had the honor to talk to several people who work at labs, epidemiological labs, that were like, actively looking for strategies to combat COVID. And they told me that they had never seen anything like this, that this is like actually a new idea to them. And also that one of them said, thinking about the graphs I'm going to talk about gets his creative juices flowing about what possible structures of graphs are out there. So yeah, I don't know. That's exciting. This is a new idea. So what is this idea? Well, here is the problem, that when you are in a highly interconnected world, you have the situation that if there's a pandemic, the growth of the pandemic is going to be exponential. As I said, when you have a small world or when you have a scale-free network, either case, it really quickly becomes exponential. In other words, if you have like random edges in pretty much any graph, you'll start to have exponential growth. It's just like really difficult to get rid of exponential growth in and of itself in like empirical networks. However, there is an interesting clue from history, which is the Black Plague. And if you look at kind of the records, it actually took a while to go through the entirety of Europe. Starting in the south, like in what was it, like in 1347, and going to the north all the way into 1452. So like it took about like 5 years to cross Europe. Nowadays, it would take like a couple months at most without any lockdown restrictions. It's just that fast. We're just that connected. So what was going on in there? Well, the microstructure of the graph was very likely something like a scale-free network. You have like towns, and you have like little houses and huts, and like at the level of a town, yes, there is probably some super spreaders. There's like these super strong like core nodes that just connect everybody. And in that sense, if the plague arrives to your town and there's a Sunday service or whatnot, you're probably screwed. Like the entire town is screwed before you know it. But the connections between the towns, because it didn't have the ability to fly, and transportation was relatively slow, so it actually would take a little bit of time, and that was restricted. And even in that case, like the plague was actually transmitted through trade routes, which were the fastest, longest ranging connections in that social graph at the time. And had they been like smart about like blocking particular types of or quarantining people in trade routes, they might have actually been able to contain the plague, because travel is not so extreme. Now, imagine that situation with modern communication technology. And then is when I think like you would actually be able to prevent the pandemic entirely. You would just be able to quarantine the region and just let everybody there get immunity, and then you open it up again, and that's it. The virus is completely, utterly, ultimately gone. That is the sort of thing that we want. We want to be able to, in a sense, quarantine a region of the network. Now, the thing is, we don't live anymore in this kind of like pseudo-planar graph anymore, because we're all connected in all these crazy ways. So what can we possibly do? Well, one strategy, this is not my idea, this is somebody else, is, coming back to kind of the clout score. If you have a score, a kind of like social centrality interactivity coefficient for everybody based on your patterns of movement. If everybody has a cell phone, you could do this analysis of like how is the contact network of a human society, and you can identify kind of like high pandemic clout score individuals, which is not only people who have a lot of like relationships, but also people who are like particularly central in the network. And the idea is that if you quarantine those specifically, you may only need to quarantine 5% of the population, and that you may nonetheless, break the network into these like modular clusters, or at the very least, like dramatically slow down the spread at a incredibly small fraction of the actual, social and economic cost of lockdowns. This has actually been suggested as well when it comes to like patterns of vaccination, although they use like more simple heuristics, like just number of friends, number of people you interact with. But a clout score that also takes into account the centrality of the people you interact with, is recursive, finds this equilibrium, that would be even better. It's like more effective. And I actually did run simulations for these back in the day for a class project, and yeah, found that something like a clout score for preventing epidemics was better than just counting number of friends and quarantining people in that way. Now, that is not the new idea. The new idea is scale-specific network geometry, and that is kind of like take out this idea of the scale-free nature of networks. Instead, think maybe the kind of network you're dealing with depends on the scale. And the Middle Ages is a little bit like that, where like at the local scale, at the level of the village, is probably a scale-free structure. At the global level is more like a kind of like somewhat of a small world network, but is largely just a planar graph. So at a large scale is 2D. At a very, very local scale is hyperbolic. It's scale-free. Now, this doesn't mean that we have to, eliminate, air travel or anything like that in order to achieve the effect. the fun thing, interesting thing to think about in here is, what if we don't need it to be 2D? It could be 3D, it could be 4D, it could even be 5D, at least implicitly, that the implicit embedded dimension in the network is 5D. It would still grow pretty quickly, like n to the fifth power still grows pretty quickly, but it doesn't grow as fast as an exponential. Not even close. At the beginning you may think like they're kind of similar, but after a while, they diverge entirely. So that would be a huge win. So the idea is like, well, let's identify a scale in the network where there is the largest kind of dimensional chokehold or statistical dimensional chokehold, and then apply an operation to the network to slightly rearrange the edges in such a way that you, in a sense, minimize the effective dimensionality of the network at that scale. Okay, so there's like kind of a lot of things going on in here, and I think that's why this is a new idea. Now, in the article, I actually came up with several examples just to get your creative juices flowing. So one of them is, imagine living in a toroidal planet, kind of this huge donut planet. There's actually a fantastic researcher, Anders Sandberg from Sweden, who's also a interesting like fellow trying to prevent existential risks and and so on, who has a wonderful write-up about the physics of toroidal planets. What would be the possible moon orbits in a toroidal Earth, and like what would be the gravity like, and wonderful article. I'll also add a link in the description. Okay, so imagine you live in that toroidal planet, and then it doesn't matter just how interconnected your society is, in a sense, as long as people don't, take flights between places. You could still have like very fast communication routes or like contact routes locally. But the idea is that if you identify a pandemic in that, large scale network structure, you can still just, cut it here, cut it here. So if you look at the growth of the pandemic as a function of time, it might start exponential, because locally it's kind of scale free. But quickly it saturates the torus in that kind of ring, and then the growth becomes linear. So, okay, that's very easy to deal with. You just cut it here, wait for everybody to become immunized in the center, and you have the rest of the planet. You're just completely free. Okay, well, but is there a way that is, more realistic? And yes, I think the idea is that you can basically calculate the average scale-specific network geometry for a given network for each of the regions, and that way you can identify the chokeholds. And I do have a few like concrete algorithms to do this, and what I don't have yet is basically a way for the minimal cut, or basically the fastest way of like the minimal edit distance between the network that is given and then the network that maximizes the chokehold or minimizes the dimensionality of the chokehold. And that is still something that I didn't fully work out, but I think it's doable. And if there weren't that many projects going on in my life, I would love to spend some time, writing a Python library in order to, maybe, enhance something like network X in order to allow people to just compute, the scale-specific network geometry and also edit networks in this way. And, maybe this is not applicable today, but, maybe in a few decades, especially if we do something like go to Mars, or we inhabit other places. I think if you go to Mars, you probably want to have you don't want to be, your entire world be disrupted by a pandemic. So actually you do want kind of this modularity, but the contact network might need to have like a higher dimensionality than just 2D. And what this does is that it allows you to have higher dimensions, maybe, again, as I said, like up to 5 dimensions implicitly embedded in the network, and still get that sweet chokehold that prevents exponential growth, which is the ultimate killer here. I'll just conclude with a kind of an extension idea here, which is that if you have, like, in a sense, 2 types of things that spread in the network where their contagion patterns are like slightly different, let's say some some ideas on the one hand, and maybe some viruses on another hand, kind of like memes and DNA. Um, the particular chokeholds, dimensional chokeholds that you have, may be very effective for one but not for the other. And I actually suspect that if you were to look at, the kidneys or the, pancreas or even, the brain and the heart, that like the actually, the microvasculature, the way in which fibers are connected and all of those, cellular networks, I think they're optimized so that you do maximize the ability to transport nutrients while you minimize the spread of things like cancers and viruses and other things that spread. And that's a difficult thing, right? Because you're kind of trying to maximize connectivity in one sense and minimize connectivity in a different sense, and overlapping them together. And I think we will find this to be the case in biology, that in a sense, biology is already trying to optimize the scale-specific network geometry. Now, I don't know if this is true, but I would put it out there as an interesting research direction. And I think that's about it. If you want to have me, go into any particular quality computing article, content on QRI, or honestly, pretty much anything at all, feel free to ask me in the comments. I am accepting suggestions for topics to discuss, and yeah, we'll see how that goes. So, infinite bliss, and have a wonderful, wonderful day.